This is an explanation of the calculations for part 2 of our chemistry lab. What's going on here is you're adding a piece of hot metal to some cold water in your calorimeter. Your goal is to find the specific heat capacity of the metal, the molar mass of the metal, and the identity of the metal. So first of all, the equation that describes what's going on here is negative Q of the metal is equal to Q of the cold plus Q of the calorimeter. Again, Q of the metal is the thermal energy being transferred into or out of the metal piece of metal. Q of the cold is the thermal energy being transferred into or out of the cold water. And Q of the calorimeter is the thermal energy being transferred into or out of the calorimeter. Here, the equation that describes Q of the metal is specific heat capacity of the metal times the mass of the metal times delta T of the metal. Q of the cold water, specific heat of the cold water times mass of the cold water times delta T of the cold water. And Q of the calorimeter is equal to the calorimeter constant, which you figured out in part 1, times delta T of the calorimeter. So if we substitute in for what the Q's mean, we get this equation right here. And if we rearrange this equation, solve it for the specific heat capacity of the metal, which is the first goal in this part of the experiment, we get this equation right here. And we know everything on the right-hand side from the experiment. We can plug in and get our specific heat. Here I've just written C instead of writing out the whole world cold to save space. So this is the specific heat capacity of the cold water and so on. Oh, I did write cold there. Anyway, the specific heat of the cold water is, again, 4.184 joules per gram degree Celsius. The change in temperature of the cold water is the final temperature of the system, which we'll get from the graph again. I'll show you that in a separate video, minus the initial temperature of your cold water, which you measured during the lab. It's in the procedure. Change in temperature of the calorimeter is the final temperature, again, which is the same, minus the initial temperature of the cold water, because once more, the cold water started out in the calorimeter, so we're assuming the calorimeter and the cold water start at the same temperature. And the change in temperature of the metal is the same final temperature as these other two, minus the initial temperature of the metal, which you measured in the experiment. It's in the procedure. The mass of the cold water you measured in the experiment. It's in the procedure. The heat capacity of the calorimeter, you got that in part 1. You measured the mass of the metal in the experiment. It's in the procedure. So you should have everything you need to plug into this equation and get the specific heat capacity of the metal, which is the first goal in part 2. Next, to find the molar mass and thus the identity of the metal, we use something called the law of Dulong and Pettit. This is an empirical law. It's something that these guys noticed. They noticed that for metals, for the most part, if you take the molar mass of that metal, grams per mole, times the specific heat capacity of the metal in joules per gram degree Celsius is equal to 25. So all you're going to do is rearrange this equation, find the molar mass is equal to 25 divided by the specific heat capacity of the metal, which you got up here in the first part of part 2.